Hello everyone, this is Luboš Pirkl from CFD Support. Welcome to the webinar about automated meshing in TCFD. In today's webinar, we would like to show you some basic principles for automated meshing in TCFD using SnappyHex Mesh. I hope everything works well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and the recording will be made publicly available. At the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar and we will gladly answer them. There is a little question form in the menu. You can ask your questions. It will be our pleasure to answer them. And yeah, I think we can start. So, okay, so this is webinar speakers. Please let me introduce us. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support and my current job here at CFD Support is telling the world about us. And I'm here in our Prague office with my colleague, Radek Máca. Hello, Radek.
Hello, Luboš, and hello to everyone who is watching us.
Are you ready for the webinar?
Yes, I am ready.
Okay, so I will go ahead. So thank you. I will only note that Radek is our head engineer and senior developer here at CFD Support, and today he will take part of the technical part of our presentation. Here's the agenda of today's webinar. The webinar is going to take about 1 hour. There will be a few sections. In the first part, there will be short introduction about TCFD and our company. In the second part, there will be a live example where Radek is going to present the core of today's webinar, which is an automated meshing process in SnappyHex Mesh from our point of view. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions and we'll do our best to answer them. Some questions will be answered right away in the webinar. The rest will be answered via email later after the webinar. So you can be sure that all the questions will be answered. Okay, so I will start with a little introduction. So our company is called CFD Support. We celebrate 10 years this year. Our headquarters is located in Prague, Czech Republic. CFD Support deals with engineering simulations and mainly with computational fluid dynamics. CFD Support provides a wide range of services in the CFD field. We deliver consultancy projects all across the CFD field. CFD Support was originally founded as a consultancy business for OpenFOAM, so we deliver OpenFOAM training. We provide technical support and custom code development. And a few years into the consultancy business, we felt that our clients deserve something more, something which helps them to be very effective in their simulations. So we decided to launch a completely new project, a software product, a CFD code called TCFD, and we have put all our skills, all our experience and our passion into it, and today our mission is developing the simulation software with the best value cost ratio in the whole market. It will be our pleasure to show you. So I will start with what is TCFD. So TCFD is a comprehensive CFD workflow which successfully merged the benefits of open source with the benefits of commercial code. So due to the open source nature, it's unlimited, it's extremely flexible, and due to the commercial code nature, it has graphical interface, it has professional technical support, it's robust, it's accurate, it's automated, it's well tested, and it's ready for use in the industry. Yeah, so this is what you can see now. This is how the graphical interface looks like. The user can do everything here from the simulation setup on the left-hand side to the simulation run and detailed post-processing of the results. And of course, besides graphical interface, there's also batch mode available, and TCFD can be run by another software, for example. About the main applications, TCFD core business has always been turbo machinery simulations, for example, pumps, many kinds of pumps or all the pump sizes, both radial and axial pumps, and also fans and blowers, hydro turbines, also compressors, or turbochargers, and wind turbines, for example. Later, what had worked so well in turbo machinery field, we decided to extend for the external aerodynamics to simulate cars or the aircraft. And nowadays, TCFD also simulates the internal aerodynamics, for example, valves or hydraulic valves or various manifolds or piping systems. TCFD is also capable to simulate propellers and ship hydrodynamics, or lately TCFD can simulate the wind loads acting on the surface of the building. So those are the applications. TCFD is from the beginning developed in a way to fit the modern engineering workflow. It's fully automated and it can be used either as a black box, so the user puts the data in, TCFD does its job, and the user just picks up the results at the end, or TCFD can be used as a highly sophisticated software where all the options are open, and the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. TCFD is from the beginning developed in a way to fit any existing workflow. It has strong integration ability because it has strong interfaces, and it's very flexible. So as you know, in every enterprise, the engineers usually have some existing workflow already, and TCFD is capable to fit in it, no matter what design tool is used, no matter what CAD tool is used, no matter what meshing tool is used. TCFD is still here to fit any workflow, to do the simulation and deliver the results for the user's judgment and for further structural analysis or for optimization, for example. So TCFD is very flexible. TCFD goes very well together with complex workflows, optimization loops. It's scriptable. It has trial version available. Real tutorials based on real projects we did in the past are available. So the start with it is quite smooth. And yeah, that's about it. I have a few other notes. So for example, we believe in the importance of technical support. Support is coded in our DNA. It's also in the name of our company. For 10 years, we have supported the engineers in achieving their goals. We are obsessed with professional technical support. We have special process for it, which is powered by the OS ticket system. TCFD is natively compiled for Windows and Linux operating systems. No need of any virtual systems at all. The engineering workflow is exactly the same on both systems. Our typical user does the case setup and the first tests in the Windows, and then he moves with TCFD on Linux clusters to use it on multiple cores to fully benefit from the fact that TCFD is unlimited of the number of users and cores. TCFD includes an automated meshing system based on SnappyHex mesh, and also the external meshes created in another software can be loaded. We always leave this mesh choice decision up to the user. So some users prefer automated meshings, the other users prefer external meshes, and they load them. So that's fair enough. We fully respect that choice of our users. TCFD has strong post-processing. Every simulation that is executed in TCFD has its own HTML report with the results. Volume fields are visualized in ParaView. Integral results are saved in CSV files to be saved in a database. Well, as you know, any software is never finished. TCFD is under continual development. The development of TCFD is user-driven. We continually gather the requirements from the TCFD users. We evaluate them and we keep adding them to the new TCFD version releases. We use a special system for code development in a team called GitLab. Well, I have a few TCFD project examples to show you in action, TCFD in action, and I have prepared a few of them, but today I think we have quite a lot of things to show you and tell you. So I will quickly go through, or I will skip them actually. So that there's proper benchmark, file benchmark, compressor benchmark, then parallel scaling benchmark, some external aerodynamics, aircraft, optimization with cases, study 1, study 2. I will skip them. I'm sure you are looking forward to Radek's part, so I will skip all these, and I will almost finish my introduction with yeah. So as you have seen, maybe some workflows here. So as you have seen, TCFD is able to fit any existing workflow, and there may be hundreds of CAE tools out there in the market, and the number of their combinations is almost infinite. And everyone can, with TCFD, everyone can create his own workflow that fits the best his purposes, skills, needs, or resources. So TCFD is under continual development. Speaking about this year, in April, we introduced the latest version, current version TCFD 1904, which is current version right now, which is actual updated. We have introduced it with many interesting capabilities. The next release will be out by the end of this year, where will be, for example, the support for heat transfer flows and many other new features. Some of them are still in the development, so let's see what we will prepare for you. And if we take a look even more into the future, we have big goals. We are really excited about them. By the end of 2020, we will introduce TCFD as a CAE platform rather than just a CFD code. We will introduce a modern CAE engineering simulation platform that offers a complete engineering workflow, including CAD, including CFD, including structural analysis, and all of them will be based on smart connection of open sources. The whole workflow will be managed by the automated master process, which communicates the results with the database, and TCFD will still keep its modularity, and it will be able to be used inside any other workflow. And regarding this, we have now two ways of development. It's the horizontal one, which is adding new tools, new simulation plugins, and the complexity, and the vertical development, which is adding new applications, new capabilities, and new high-tech methods for the plugins. Okay, so now I have finished my current part right now, and it's time to switch the presentation to Radek. So Radek, may I ask you whether are you ready to take your word?
Yes, I'm ready. Hope you can hear me.
Okay, we can hear you very well. So right now I'm handing over the presentation over to you. So
okay, perfect.
in a
Thank
few
you.
seconds, okay, in a few seconds, you should take over. So Radek, thank you for being with us, and good luck with your part.
Yeah, thank you, and thank you too for your introduction, for a nice first part, part of the webinar.
And okay, so we are excited and we can't wait your presentation. So go ahead. We can see your screen. You can go ahead.
Okay, perfect. Okay, so thank you, Luboš, and hello again to everybody who is watching. So I have prepared a presentation using which I would like to show you the basic principles of meshing with TCFD, and behind the TCFD there is a SnappyHex meshing tool. So let's start directly with the presentation, and I will show you one simple live example and all the other parameters and the principles I will show you in this presentation. So today I will focus directly on the inputs and on the workflow for the mesh generation. So in general, as Luboš has already mentioned, that the TCFD is prepared for both external meshes or for STLs, just the input the geometry, and the mesh is prepared within the TCFD workflow. So I will focus today only on this first line. So the generation of the mesh using the STL geometry using the SnappyX mesh, which is behind the TCFD. What we would like to always keep in mind that if we put something wrong at the beginning, we get only the garbage at the output. So we have to focus on this important aspect of the input data. So what does it mean? What are the requirements for the STLs? So at the beginning, we have to generate the STLs in any CAD software or any software you like. And these STLs can be put inside TCFD and prepare the mesh using these STLs. So what is the important parameters? They are listed here and we will go one by one. So first one is the flow path geometry, which is obvious. So we have to provide the STLs which describes the wet surface of our machine or our geometry, using which we will be able later on to prescribe the mesh parameters based on each STL. Then very important parameter or requirement is the simplicity. So the geometry should include just the important details only, which means that any details which may not affect the overall machine parameters or overall efficiency or overall parameters or results should be neglected from the geometry, because if you include them and they don't bring anything new to the flow, then it only makes the mesh generation process harder and you have to use more cells and so on. So any detail do increase mesh requirements, but also increase the simulation cost, right? So I like this statement, which holds in daily life, but here it holds particularly. Everything should be made as simple as possible, but not simpler. So it is easy to say, but hard to do, right? So what should be neglected and what cannot be neglected at all. Okay, then the component thinking. So when we were developing TCFD, we like this approach of the component thinking because each geometry, each rotating machine or any other machine consists of components. So we always think in components. As first splitting is of course stators and rotors. So what is rotating and what is not rotating, and each group can be also split into lower parts like pipes, volutes, diffusers, virtual tunnels, rooms, and rotors, of course, impellers, propellers, and wheels. So this brings that you can define each component separately, generate mesh separately, and then all put together to generate a full geometry. What is an advantage of this splitting is that then you can then automatically evaluate all the integral quantities which are important for the particular application at each interface between two components. So if you have, for example, 5 components which build your geometry, you can then evaluate, for example, the pressure path flow or path flow for any quantity, so you can see the progress of the total pressure through your object, for example, through your machine. So therefore, the splitting the geometry into more components could be convenient. So simple example what I am talking about. So this is the example of radial pump. So this is the input, let's say, geometry, the wet surface geometry. And to think in component, we can split this geometry in, for example, into 4 parts. Let's say inlet, pipe, impeller, volute, and outlet piping. If we do this, we can put all together, we can generate the mesh separately, then put together and simulate it as one machine, as one mesh. So each component holds a separate computational mesh, which is imported or generated by TCFD. So in these examples, I I will show you how to generate the meshes and what are the requirements of the interfaces and other parameters. So now if we focus on a particular component, so the component has to be split into physical boundaries, because in CFD at least we have to prescribe what is the inlet, what is the outlet, what are the walls, which are rotating, which are not rotating, which are moving, and so on. So it is not enough to have one STL for one component, but to have several STLs following the splitting of our geometry, basically the splitting for prescription of different boundary conditions or boundary types. So at least we have to, for example, for rotating, for impeller, we have to distinguish the following parts: inlets, of course, outlets, blades, hubs, and shrouds, for example. And for detailed tuning, for finer tuning of mesh parameters, for example, we would like to have the leading edge much more finer than the rest of the blade, then we should also think about the splitting the blade into meaningful parts. It is not compulsory, but can be an advantage. So for example, we can split the blade into 4 parts: leading edge, trailing edge, pressure side, and suction side. And then we will be able to really play around with the mesh parameters with the setup. Okay, so each component has to have it, not each, for example, the closed room is not, but for internal flow, for rotating machinery, for example, each component has its own inlet and outlet, and to connect several components or to neighboring components, we have to properly prescribe the interfaces and align them correctly. So this is important for connecting neighboring components. So this alignment has to be perfect. This is just a, for example of the inlet outlet alignment between the impeller and volute. So each component has its own interface, and this interface has to be aligned perfectly. So there can be no extension from one side. So the inlet from the inlet to the volute has to have the same patch, let's say, or same geometry, same STL as the rotor outlet. Not same in the, let's say, in the STL sense, but the topology has to be same and has to be at the same place. So this is important to know. Similarly, because TCFD also allows to simulate just the segments of the wheels. So for this, for example, Francis turbine, you can use just the one blade segment, and then it holds the same. So the virtual interface of the full wheel has to match accurately. Then I think this is the last property I would like to mention, is the watertight property. So the STL, because if you split the geometry into several parts, then sometimes you generate each part separately, and these, for example, these parts don't see each other, and then you can get something like this. So the mesh which is not waterproof. So if you would like to be really sure that your input geometry is okay for the meshing, then you have to generate, or you have to at least try to generate the waterproof geometry, also so-called node-to-node geometry. Or you can also generate some STLs with the tiny holes. The holes are really tiny. What does it mean? If the holes are much more smaller than the resulting mesh at these parts, then it's also okay for snappy hex meshing. But keep in mind, you have to, if you want to be sure, you need a watertight geometry. Okay, so it was not the last one. I hope maybe this is the last one, because the STLs describe not an analytical shape, but it is the first for discretization. So you have to provide fine enough triangulation, otherwise you will simulate something which is not the same as you intended, right? So you don't have the circle at the inlet, but you have just the polygon, for example, or the blades are zigzag and not smooth. So be sure that the triangulation has to be, or you have to generate it in that way that the triangulation is always finer than the resulting computational mesh. Yeah, because you have to be as close as possible to the smooth shape of your geometry. Yeah, just one of the what you can get if you make the triangulation really rough. So for example, if you zoom to the interface, then because at the interface some interpolation is made, and if there is a big errors in the matching, then you can get also the big numerical errors by the interpolation of the interfaces compared to the fine triangulation on the left side. So keep in mind also this. So this was the general requirements, and now we can focus on the meshing itself. So because behind the TCFD we use the snappy hex mesh meshing tool. So just for those of you who don't know the snappy hex mesh, so it is a robust open form application for hexahedral dominant mesh generation. The mesh generation consists of three main phases. So it starts from an initial mesh. It's called the background mesh. So the mesh consists of hexahedral cells only, and from this mesh, the meshing starts. First is the castellating phase, so it follows your objects, refine based on the given parameters, and at the end of this phase, it gets rid of the cells which are not in the place you would like to mesh. Then there is snapping phase, so there is no splitting of cells, and it just attracts the points to correspond to the surface geometry. And at the end, you can add the layer phase to the snapped part of the mesh. So these are in a quick way the basic steps of the SnappyX meshing. Okay, now let me show you a very quick live example how quick we can generate the meshing using TCFD. And for those who are using just the SnappyX machine standard open form, you can see that sometimes the process is very painful. You have to edit a lot of files. You have to be careful to do it really carefully and without mistakes. So now I'm opening TCFD and I would like to mesh a simple piping geometry. So first of all, I will save my setup because everything you do, it can be anytime saved and keep for the later usage. So I think I have prepared the geometry here. So for example, mesh setup. So I'm not going to run the simulation, but only to generate the mesh. Okay, so first of all, I will just check how many processor I will use. For example, 4 processor for the meshing, and now the meshing itself is done in the component section. So in my case, I have one multi-solid STL files which includes all the parts of my piping. So I will quickly load it. So I have it here, this pipe STL. So I can load the geometry. Okay, I can anytime after the geometry is loaded, I can visualize my input geometry by clicking on this component. So this is my simple geometry consisting of 3 parts. So what I have to do, so set some refinement at the wall or at each part. So for inlet, the type is inlet, and I don't want to have any refinement, for example, at the pipe outlet. Let's say set it as outlet, and also I don't want to any refinement, and on the wall I would like to have one level of refinement. Then I have to set the background mesh, which is the largest cell in the mesh. So I'm not sure the dimension, so let's try 5 centimeters. Now I can visualize the background mesh. Okay, it's too rough, so let's go for 5 millimeters. Okay, it's better. Oh, let's say to make it really quicker. So 1 centimeter will be the basic cell size, and I have to also put the internal point inside. So this is inside point which tell us which part of the mesh should be meshed. So I would like to mesh the pipe from inside. Okay, that's all, and I think all the parameters or the basic parameters are set. So I can go for the meshing for the TCFD manager. So I will apply TCFD manager. Okay, it tells me that I'm simulating fun, so I will switch to stator because I have no rotor defined. And let's go. I will write the case and run the meshing. Let's mesh it all, and now based on my setup, behind it creates all necessary files. It runs all necessary applications of OpenFOAM, and at the end we will see here our generated mesh, and that's all. So there is no need to provide a snappy hexmeshdict files and other files, other helpful for additional applications. So my mesh is generated now, so I can close this, and this is my mesh. To see the basic parameters of the mesh, I can quickly generate the light report, which includes also the mesh parameters, so overall amount of cells and some quality parameters listed here. And basically that's all. Of course, for more complicated geometry, it takes more time because you have more boundaries and you have to go step by step. But for simple geometry, you can get mesh pretty quickly. So this measures just 34,000 cells. We have no y plus values because we haven't run the simulation. And yeah, this is the topology, and the mesh details. Here are some parameters like non-orthogonality, aspect ratio, skewness, and so. Yeah, so in few minutes, I am able now using TCFD to generate a mesh, of course, for simple geometry, but the principles are clear, I think, now. So let's move on. So let me quickly describe the parameters for meshing. So first on, the basic parameters are as follows. So for each boundary, I can prescribe the minimum and maximum level of refinement. What does it mean? As I already mentioned, the meshing process starts from the background mesh. So I can define the background mesh size, which corresponds to the largest cell in the mesh. And all the levels here just tells how many splittings will be done of your background mesh size. So if my pipe wall intersects the background cell, it will be splitted just once. So to have cells at level 1 with a half of the size. Yeah, the dimensions are basically given here by the scale factor. It means, for example, if your input geometry is in millimeters, you should tell here that your input geometry is in millimeters. So minimum and maximum level of refinement, then the layers. So at the end of the process, the boundary layer will be added, and you have to tell the mesher which part of the geometry you would like to mesh, if inside of the pipe or outside of the pipe. So, and basically this is what you need for the simple meshing of the simple geometries without any other features. So basic parameters. For example, you can play around. So this is my piping, and you can really play. So if I set the background mesh to these values without no refinement, I will get something like this with this amount of cells. So I would like to save some cells because we are always in 3Ds and it is really hungry for cell amount if you would like to have your mesh really finer. So I would like to focus that I need to have a finer mesh at the walls because to follow the Y plus criteria and other. So I would like to save some cells inside so I can I can set the background mesh I can double the size of the background mesh to 0.005, but I would like to have the same refinement at the wall as in previous case. So I will set here 1, and I have the same topology at the wall, but rougher mesh inside. And I save here 500,000 of cells, for example. And similarly, I can go to the rougher mesh. Of course, always it depends on the application, what you are intended to get from the simulation, of course. TCFD includes other features. You can, for example, play with the background mesh positioning, because it's initial mesh for your snapping. So let me, okay, where's my component here? So you can play also around if you apply the advanced options. So you can play, okay, show background mesh. You can play with the positioning of the background mesh. Yeah, sometimes it can be clever to somehow positioning the background mesh to follow your input geometry. So it can be done directly in the GUI. So example of mesh positioning. You can also define a cylindrical background mesh based on the simple parameters. So the cylindrical includes, let's say, 3 radius for the topology of the cylindrical hexahedral structured mesh. With the cylindrical radiuses you define, cylindrical grading, for example, to create inflation layer or boundary layer directly within the background mesh, and the cylindrical warp just changing the topology of the inner rectangle from the rectangle to the circle. So the best way how to play with them is to simply try. Yeah, so you can also define the cylindrical background mesh for example, axial machines. Okay, then advanced meshing parameters. So an usual problem could be how to mesh small gaps in the geometry. Yeah, so for example, we have the clearance part for this compressor segment geometry, or you have just tiny shape between the trailing edge and the outlet interface and so on. So how to treat these obstacles? So TCFD allows or offers you a feature using which you can define the gap between 3 type of gaps. Gap between leading edge and the inlet interface, gap between trailing edge and outlet interface, and gap which is the most which we can see through our turbo machinery project is the clearance part. So there is just tiny gap between the blade cap, so between the blade and the shroud. So how to mesh it properly? So first option and the easiest option is to have the geometry split it, or the blade split it into these inlet, into this leading edge, trailing edge, suction side, pressure side, blade cap, and so on, parts of the blade, for which we can set them as a type following their meaning, and then to prescribe the blade cap gap as a in meters or in millimeters, depending on the input dimensions, and then TCFD automatically sets the proper level of refinement to mesh these gaps. Yeah, so we just set some values at blade cap, but if we provide also the blade cap gap, then it automatically remesh these parts to have finer mesh only in these gaps, and to have rough mesh apart from these gaps to save a lot of cells. So for example, there is an example of such a meshing, and we have something around 400,000 cells. Okay, what about if we do not have the splitting? So if we have just the blade, so if we set the basic setup without the blade cap gap, because we can't provide it if we do not have this blade cap, so then we find that the meshing is too rough to capture this gap between blade and shroud, and we get the hole. So one option is to refine the whole shroud to higher level of refinement. So from, let's say, from shroud 1, we need to have level 4. So then, okay, this remeshed correctly, but we have too much cells only for shroud meshing, and we spent more than 1.5 million cells just to mesh the shroud, which is not good. Similarly, we can refine the blade. Yeah, we have only one STL for blade, so we can refine the whole blade similar we set to 4. Okay, but we have 3.5 million cells just about to capture the gap between blade and shroud, which is also not good. So we have implemented a feature which can save the situation even you have only one blade geometry. This is this use gap refinement feature. So if you enable it in the advanced menu and set the high level of refinement, so here is enough, 4 is enough for the part of the geometry between in between them, or for which the gap is basically, yeah. I'm telling it in more in complicated way. So just because we would like to measure the gap between blade and shroud, so if we set this gap refinement for these parts, then the Snappy knows how to find these gaps and refine them locally. So we can just define these parameters, and as you can see, we also have a nice meshing of just of the locally of the gap, and spending just 400,000 cells compared to these millions with the standard setup. So use gap refinement, locally refine the mesh up to the preset level in gaps between surface for which the gap level is defined. I have written here, so I don't know why I'm I'm composing poets here. Okay, so this was the gap refinement. Then other feature is simple feature is refinement per region. So for example, for external car aerodynamics or external aerodynamics in general, or if you would like to remesh some part of the some part of your geometry for which you don't have STL, you can define the simple shapes like box, sphere, cylinder, and define the remeshing inside or outside from these closed objects within your geometry at any place. So this is, I think, clear. Then very very important parameters of the mesh is boundary layer. So let's start from the very beginning. So in the components part, you can define per each part, excluding the inlets and outlets, of course. You can define how many layers should be added at these places. So there can be different numbers for different parts of the geometry. And then if you would like to define a local parameter or the parameters of the layers itself, so you have to go to the advanced meshing options, SnappyX mesh menu. In the part of the adding layers, you have to define, or you have to redefine, because there are always default parameters, the sizing of your boundary layer. So you can set different number of layers for each boundary, and boundary layer parameters, which is this, like expansion ratio and first layer thickness, for example, are common for the whole component. So what does it mean? Each the parameters, so relative sizes, if you enable the relative sizes, then these parameters are relative to the cell at the wall or at the patch to which you are adding the boundary layer. So you can see that the boundary layer is extending based on the cell size, the original cell size at the wall. If you uncheck this option, then these values are in absolute, so in meters, if your input geometry is in meters, and then it holds the same sizing for the whole patch. So this is the relative and absolute. Then the parameters itself, so you can choose how to set the parameter of boundary layer. So expansion ratio is the ratio between two neighboring boundary layers, and always you need to have two parameters. And the second parameter you can choose if you would like to set the final layer thickness, which is the last layer in the layer, first layer thickness, so the smallest thickness at the wall, or the whole boundary layer, which means the whole boundary layer. So you can define it using these parameters. Another important parameter for adding boundary, except the others which are, let's say, super advanced and doesn't bring much better adding layers phase. So this boundary layer is this parameter is feature angle, which tells you above which alpha in this sense the boundary layer should collapse, because Snappy Xmesh always prefer the mesh quality than the 100% 100% of boundary layer edit. So for example, if you would like to collapse edges at the sharp angles, so then you can set this feature angle to the default one. Or if you would like to keep the boundary layer also at the sharp edges, then you should increase this parameter. Minimum thickness, it is important. It is obvious that if the boundary layer which Snappy would like to add is less than this value, then it collapse the boundary layer at all. And the remaining parameters are set to default best practice values. You can play with them, but it's really experimental, and maybe for some particular application may increase the quality of the boundary layer, but for another one it may be much more worse than the default values. Yeah, so it's pretty experimental. So just show me an example. So here we have meshing option. We have a simple Excel fun geometry. So the mesh refinement and the walls are 3, and we would like to add 5 boundary layers. So just here's an example how to use relative or absolute sizing. So the background mesh size is 2 millimeters set in this case. So if you set this level to the same levels, then you can find the equivalent setup for both relative and absolute sizes using a simple computation. Because if you compute the sizing of the cell at the wall, which is simply 3 splitting of the cell of this size, so you will get something like this. And if our first layer is 0.2, it means that in absolute values it is 0.05. And if you do the meshing with both these setups, you can get the same mesh. Yeah, so this is the boundary layer edit at the axial fan blade. So this is example of one slice, and you can see that at the trailing at the leading edge, which is pretty smooth and not so sharp, the boundary layer is edit properly. But at the end, where the trailing edge is really sharp, so it is almost impossible to add boundary layer with a good mesh quality. So then Snappy Xmesh decide to collapse the boundary layer near the trailing edge. So this is the property of the Snappy Xmeshing which we have to count with if we use Snappy Xmesh. So this is the example of our boundary mesh. So what will happen if we set minimum level to 3 and maximum level to 5? It means, okay, refine the shape or refine the mesh in the highly curved parts of the blade. So then we get something like this. So if we use the absolute value, so it means keep this sizing everywhere, then the boundary mesh collapses at the parts of the refined mesh, because there is no place to add such a big boundary layer. So then you get something like this, which is maybe not convenient to get. But if you enable the relative sizing, then the mesh is properly added at all the parts and also at all the refined parts. So you have always keep in mind that, okay, absolute values is fine because you know the sizing of the mesh, but for the parts which has different sizing of the cells, then you should go for relative sizing, because you will be sure that the boundary coverage will be more successful than for absolute values. Okay, so this was the boundary layer example. Then we have an example for interface meshing, because it's also important and can improve your mesh quality and your results. So interface matching is very important for overall accuracy. So this is basically done by the input STLs if the STLs match perfectly. And then the meshing parameter of the neighboring interfaces should be similar to have, let's say, the same amount or the same topology of the mesh at both sides of the interfaces. Because as we already said, there is made an interpolation, to get the values from one side to the other side. And therefore, if you think about the meshing, then you should keep in mind that the best way is to have the same sizing on both sides. So this is the example of radial pump. For example, in the inlet pipe, I would like to have pretty rough mesh. In the impeller, which is the most important part, I would like to have quite fine mesh. And in the volute, which is something between, I would like to have some medium refined mesh. So I have different sizing of the mesh. So if I do it in the clever way and I adjust the surface level refinement for the particle interfaces, I can simply get a nice matching of the mesh at these interfaces, between the impeller and volute and between the inlet pipe and impeller, for example. So this is, let's say, the best we can get from Snappy. Of course, if you don't follow this rule, you will also get a good mesh for simulation, but also the interpolation, you lost some information. So sometimes it's not so important. For some simulation, it can be important, which can affect your results significantly, for example. But this is, I think, this is not the case. This is still good, but not as good as the previous example. So this is the meshing of the interfaces. So now let me quickly describe some advanced SnappyX-Mesh parameters which can be set within the meshing options SnappyX-Mesh part section in the TCFD GUI. So SnappyX-Mesh parameters can be found in the advanced section. So you have to enable the advanced section and then go for this section. It is divided into several subsections based on each step of the meshing process, and each subsection defines parameters per component. So don't forget that if you set, for example, add layers for component 1, then you have to also switch to component 2 and set the similar or different parameters, but it must be set per component, for each parameter. So first one you can set is, for example, feature edges included angle, which is a feature which is run behind, which generates so-called feature edges, which helps the SnappyX-Mesh to snap the mesh better to the sharp edges, and also you can use it for the local refinement at these edges. So this is example. If you for example set 95, you get something like this, and if you would like to also get, for example, this edge, you have to increase this feature angle. So this is pretty simple and obvious. In this section also you can enable a surface hookup, which is the, let's say, not the first 8, maybe the last 8. If your input geometry includes big holes, and usually if your input geometry is not waterproof and includes big holes so that the mesh leaked out from your object, so at the end you will see some error after the meshing, and if you visualize the mesh, then you can see that the mesh is made from both sides of your geometry. So this is, let's say, the last 8 which can help to fix these gaps. So if you enable it and look at the surface at the beginning and at the end, it can save the situation and patch these holes. But be careful, always check the surface after this hookup, because sometimes it patch the mesh or patch the input geometry pretty nicely, but sometimes it distort the shape totally. So sometimes it can save the situation. in case of not watertight property geometry. Okay, and other parameters based on which affects the, let's say, adding or splitting the cells. So first two parameters are the global and local cells, which define the maximum number of all cells during the meshing process. So I think that our default values are 10 millions, but if you intend to mesh some big complex geometry, or really you need to have really fine mesh, then you should, and you expect more than 10 million cells, you have to increase these numbers. I think it's from historical point of view, when the memory was not in gigabytes or not in tens of gigabytes, and it's say the situation to really keep the amount of cells in the given values and not to exhaust the computer. So this is the maximum number of cells, minimum refinement level of cells, because it works in iterations, and at each iteration Snappy decide how many cells should be splitted, and it can stuck in the loop, for example 50 iteration just for splitting 5 cells. So we can tell, okay, if only 10 or 10 and less cells are denoted for splitting, okay, stop the splitting process and go on. Max flow unbalance is some default parameters for rebalancing during the meshing if you run the meshing in parallel. Yeah, so it's just some input parameter which is there is no need to change, and this is, and let's say okay value for general applications. Then there is more important parameters which is called cells between levels. So which tells the Snappy how many cells, how many kind of cell layers should be used between two different levels of refinement. Yeah, so you can see if we set 1, then the transition to the rough mesh is pretty quick or sharp. But if you use, for example, 7, then the transition from the finer mesh to the rough mesh is much more smooth. Of course, you have to count that we are always in 3D, and it is really hungry for cell amount. But the mesh is then much more smoother, finer, and nicer, but you can get a lot of cells. Feature edge levels, feature edges level. So as I already mentioned, you can define the mesh refinement based on the edges, which are automatically generated somewhere here, right? It was here. So to these edges, you can set the level of refinement, and it can also, in some situations, some particular application, it can generate nicer mesh for your particular application. So this is example, if the level of on the surface is 3 and we set 0 or up to 3, we get this one, no refinement at the edges. But if we set the feature edge level to 5, then we can see that we have 2 more levels at the edges, at these edges. Okay, I think it's a piece of cake. And the last one is the resolve feature angle, which is the angle using which the Snappy decides when to apply the maximum level of refinement. Again, it uses this, in this sense, this parameter. So if we increase or decrease this value, then for almost all curvatures, the maximum level will be applied. If we go for higher values, then only at really highly curved part of the geometry, the mesh refinement will be applied to the maximum level. I think it is also obvious. All right, and then there are many parameters for the snapping. This is just the parameters include which affect the algorithm itself, and it is set basically to our best practice values. And you can also play around, but it is also per case, and there are no significant improvement of the mesh quality of the meshing process. But for some case, you can get some better values. And also the mesh quality parameter, there are many of them, and this is also set some best practice values which we use for all our projects and all our all our work. So we do not suggest to change them, but if you are an expert in it, you can really play with these parameters. Okay, and maybe the last thing to mention is the mesh quality check. So this, if we can talk about this, we can talk hours of the mesh qualities and mesh topologies and so on, but this is not the purpose of this webinar. Where to check the mesh quality? As I already showed you at the beginning, TCFD generates a report which includes these mesh statistics like amount of cells, y plus at the end of the simulation, and the detailed parameters values for each component. So I picked three main parameters. First one is the aspect ratio. So aspect ratio is just a proportion of the shortest and longest edge of the cell, and usually we get high values appears in very fine boundary layers, which usually Snappy can't generate, for example, aspect ratios like hundreds and thousands. You get this aspect ratio usually for the hexahedral structured mesh, and it doesn't affect let's say the accuracy too much, but it affects convergence, for example, of the pressure equation solving. So you can see then that the solver uses more iteration, and which implies that the simulation takes more time to converge. Skewness, again, higher values may impair the accuracy and always depends on the application, but there are no threshold where the simulation will crash. Yeah, so we can simulate, we have nice results with the mesh which has skewness more than 20, and still the results are okay, the overall results. But for some particular application with y+1, if you really focus on the recirculation areas, then it may affect the results, of course. And the last one, the non-orthogonality parameter, which affecting both accuracy and stability. So let's say there is a safe range. If the non-orthogonality parameter is less than 70, that it's safe range for usage and for applicability. Then between 70 and 90, you have to be careful. So sometimes it requires special treatment, like enabling non-ortho correctors, which can be enabled in the solver setup. And if the non-orthogonality is higher than 90, that is bad mesh, and this cannot be used for simulation. And usually the solver crashes for these meshes. Okay, so let me conclude. I know I do not have. Okay, yeah, it's almost 1 hour left. Oh no, gone, not left. I don't want to scare you. So let me conclude. So I have written down some buzzwords, what should be followed when you generating the mesh. So first one, have a perfect STLs. So do not have the garbage in, but you should have the perfect STLs as the input. So for example, high resolution, watertight, enough boundary splitting, avoid sharp edges and tiny gaps, because usually sharp edges are always problematic to mesh and brings a lot of problems. When you starting the meshing process, so start from a rough mesh, because if you start from the rough mesh, you can see the result quickly and you see the basic mistakes. And if the rough mesh is okay, then it's good time to refine the mesh at your desired places, or to remesh the mesh by decreasing the cell size, the background cell size, and so on. So always refine gradually and step by step to follow your requirements or requirements of your application. Adding boundary layer is a big challenge, of course, and this should be done for a nice mesh without boundary layer. So if you are done here without the boundary layer and you are satisfied with the mesh, then it is a good time to add the boundary layer, because otherwise you waste your time. It takes more time to generate, and if your mesh is pretty bad before the adding layer, then of course after the adding layer it will be much worse. And always check the mesh visually. So after each meshing phase, visualize the mesh and follow the problematic parts with the sharp edges, parts with the highly curved surfaces, and so on. So at each step, follow these parts. For example, if you have the clearance, so check the clearance if the mesh is okay or if there are some holes in it, and so on, and follow your current mesh topology. And of course, sometimes be patient, because if you have really complex geometry with a lot of boundaries and a lot of problematic parts, you have to go really step by step to get a nice mesh. Okay, so I think it's all what I would like to tell you today, and I think it's time to go back to Lubos to conclude this webinar. And that's all. So Lubos, are you there?
Yes, of course. Thank you,
Perfect.
Radek, for your contribution. It was great. Thank you.
Thank you.
I think it's time for the questions and answers. So it's time for Q&A. I would like to ask the audience to ask questions. We will pick a few of them which are most relevant to the topic, to the meshing, to this webinar, to the automation of meshing. So I would like to ask the audience to ask the questions, and we will pick a few of them, and we will answer them, and then we will conclude, and it would be it for today. Okay, so yeah, a very typical question, which is typical. People ask whether the webinar whether the recording of the webinar will be available. Yes, it will be available. It will be available on our YouTube channel. So feel free to let's say tomorrow in the morning take a look at our YouTube channel. We will publish there the recording from today's webinar. So you can take a look there, or you can download the video and watch the details if you like what you like. Yeah, and yeah, okay. Yeah, so let's take a look what we have here. We have a couple of questions here. So Radek, can you see some good question which is relevant to the topic? Is compatible with
Yeah,
others?
I see the question by Kenneth. So if this surface hookup was the feature by TCFD or by OpenFOAM, so it's featured by OpenFOAM. So this surface hookup is a utility, I guess, which reads from some special control dict, which includes just the size of gap, sizing of the gap, which should be patched, and that's all. I don't remember by heart the particular usage in OpenFOAM, but I think you can find it on the internet or in the documentation of this utility. So surface hookup, I think, is the name of it.
Yeah. Yeah, Francisco is asking whether SnappyHex Mesh is compatible with other software. Well, I think not very much, because it creates a lot of polyhedras, and as far as I know, a lot of commercial codes are not familiar with, for example, 52 phase cells like SnappyHex Mesh sometimes does. So as far as I know, when you have SnappyHex Mesh, you definitely should use some OpenFOAM based solver or solution. Yeah, yeah. Those are some other questions. Well, okay. So Radek, can you see any other interesting question? Which case Y plus represent? I'm sorry. This Torben Frenner is asking, in which case does Y plus represent an important requirement? Is adding boundary layers the only way to improve it?
Okay, maybe I can discuss about this. So Y plus, for example, is important for the for the wall functions for turbulence model. So standard wall function working in the range of y plus between 30 and let's say 300. So therefore you have to know if you are in this range for which these wall functions were built. So for this application, you have to be sure that you are in the correct range. Then there is also this low Reynolds or resolved boundary layer, which is usually about y plus around 1. So if you have a really fine boundary layer, you have to be also sure that you are around these values for really cases where for which it is important. But you can get these values after the simulation. So first you have to simulate, then you see, okay, I'm in the correct range, that's okay. If not, I have to refine the mesh, for example, in both sides, make it rough or make it more fine and use different approach for wall treatment. And so there are many applications for which bypassing is important. Hope.
Right. Okay.
Don't
Okay. Thank you, Radek. Okay. Yeah. Also, Debasis has a question. Hi, Debasis. Is it possible to refine the mesh imported from another software to TCFD? Yeah, it's a good question. It's not possible in the graphical interface. So no, it's not. And you can elaborate about that, but it's not directly possible. That's for now. But we can discuss this because it's definitely possible using some tools available. So it's for detailed discussion via email. Okay, and maybe the last question, Francesco has a question. How can you decide the level of gap refinement? And yeah, what's the approach? I don't know, Radek, do we know the exact number in advance, or do we just try it and take a look and try and take a look?
Well, we can compute it, because if you know the clearance, for example, clearance is the typical example, so the part between the blade and the shroud, and because you have the geometry, so you know this clearance gap. So based on your background mesh size, you can compute this level of refinement which follows the gap. So for example, if you would like to have 4 cells or 8 cells in this gap, you can easily count the sizing, and from that you can count the level of refinement, and you can use it in the TCFD. And you have two approaches, as I have already shown. That first one is this gap, clearance gap. So you can directly set the gap, and TCFD automatically evaluates the proper level of refinement. Or you can set it to the gap, blade cap part, sorry, as your level if you compute it by your own. Or if you use this gap level feature, so you can put there really high level, because it ends at the moment where, for example, I don't know, something like 4 cells fits this clearance, and that's the maximum level which Snappy impose, even you set the higher levels. So basically there are, let's say, three approaches how to set.
Right. Okay. Yeah, we have. Yeah, now it started to be quite long, so I suggest to answer 1 or 2 questions, and then we will conclude. So Kagan is asking whether mesh intersection surface in the rotating and non-rotating parts are conformal, and yeah, if not conformal, what does the sizing, if it has to be the same or similar? Actually, no. The interfaces, the mesh can be different. You can combine, for example, the imported mesh with the SnappyHex mesh and all these kinds of meshes, because at the interfaces we use like AMI interface, which does not care much about the structure of cells. Only the outline, right? The boundary has fit.
Yes. But in general, what I mentioned during my presentation is that it is good to have the same topology on both sides and same sizing of the cells, even the cells are not conformal.
Right. It's better. Yeah. Uh, okay. Yeah. And yeah. Okay. I think this would be it. I think this would be it. So the rest of the questions, we have a lot of questions, but many of them are very specific or off topic. So we will answer them via email. So for now, I would close this section of Q&A. I will take the presentation back, Radek, if you don't mind.
Yes, sure.
So I hope you can see my screen now,
Yes,
which
I
is the
can.
live example
Live
with
and
the
yes,
aircraft.
yes.
Yeah.
Mhm.
Okay. And I will slowly conclude. So our presentation is nearly approaching to its end. I would like to finish with a little story from the cat market. So this was Q&A, right? And I would like to finish with a little story from cat market. Maybe you still remember that 20 years ago, everyone had used AutoCAD for cat operations. Its market was great and at that time, and its position looked untouchable at that time. But times are changing very quickly. The world has changed, and nowadays AutoCAD is not that good anymore. And there are others. There are others who were small or did not even exist 20 years ago, but they reflected the change of our time. They reinvented the value for the customer, and then they made it. And they made it to deliver it to the market, and they are big now. And my point is that the same change is going on right now in the CFD market, which is the younger and nicer sister of cat market, and it's always has been a little bit behind. And this is exactly why we are here. We are here to allow this change happen also in the CFD market. So we are small now, but we hope we will be big in the future. So here are a few of those who already share our visions with us. Many others are already on their way. Every one of you is welcome in our family. The bigger we are, the stronger we are. So feel free to join us. And I think this would really be it. Uh, feel free to tell us how we can support you in your projects. It's our job and also a pleasure. And yeah, I think this is it. Radek, do you have something to say?
I just want to say thank you for watching, and I'm looking forward to get in touch sometimes in the future with all of you. And yeah, I think that's all. Thank you, and see you next time, or hear you next
Okay.
time.
Okay, thank you. So we leave you with that. And for now, we would like to thank you for your attention.